Hey there, it's Mrs. Marquette. Today we're doing 8.6, which is the last section in Chapter 8. Today we're going to be talking a lot about solving equations that have both exponentials and have logarithms in them. There are really two big ways of solving with exponentials and logarithms. The first is by looking at the bases, so we'll do that for the first page of our notes. And the second is by using order of operations backwards, PEMDAS backwards, and the fact that logs and exponentials are actually inverses of each other, so they undo each other. So looking at this first page, it says one way to solve exponential equations is to use the property that if two powers with the same base are equal, then their exponents must be equal too. So let me tell you what I mean by that. When we've got 3 to the x equals 3 to the fifth, like our bases are already the same. So if I want the entire left side to be equal to the entire right side of this equation, then really all I need is to make sure that the powers are the same too. So we can say because of this, x has to equal 5. That's just what has to happen. But if I change this, if I say now 3 to the x equals 3 to the 7, we still have the bases the same, we just need the powers the same. So now x is 7. If I change this and I make this a 71, then my x has to be 71. So if my powers are, or if my bases are the same in any of these problems, then I can set my powers equal as well. So that's kind of what this property says. It says for b is greater than 0, so I've just got b being a positive number. If b to the x equals b to the y, meaning if two sides of the equal sign are exactly the same, then x has to equal y because I already have the bases the same. Same thing happens for logs, which makes sense because logs equal exponents. If my log base b already equals my log base b, then x has to equal y because all I'm looking for is that the left side equals the right side. So let's try a few of these. Number 1 says to solve 2 to the x minus 2 equals 2 to the 32. Now notice my bases are already the same. When I write the next line, here's what I'm not doing. I'm not saying, okay, divide by 2, cancel those 2's. Not at all. What I'm saying is, okay, we already have the 2's equal. Let's just say, therefore, x minus 2 has to equal 32. So I'm not changing the problem. I'm just saying this is the part that's not equal yet. So let's work on that. So I add 2 to both sides, and I get x is equal to 34. Here is my answer. If I want to do some checking, so let's go for checking, I would say 2 to the 34 minus 2 equals 2 to the 32. 34 minus 2 is 32. So I get 2 to the 32 equals 2 to the 32. Those two things are equal. Check. So again, it's not just saying cancel out those 2's. It's saying that whole equation has to be equal. All right, looking at number 2, again, my bases are equal, so I can say set my exponents equal. 4x has to equal 2x minus 3. So this is an equation that you guys know how to solve. I subtract 2x on both sides to get all of my x's on one side and my numbers on the other side. I divide by 2 on both sides, and x is negative 3 over 2. I could say negative 3 over 2. I could always also say negative 1.5. I don't care which way you say it. You should be seeing a pattern. I've got 5's as my bases. Those are already equal. I can say, therefore, 7y has to equal 49. That's the only way the left can equal the right. Divide by 7 on both sides, and y is equal to 7. If I plugged 7 back in for y, I'd get 5 to the 49 equals 5 to the 49. Check, we're good. Now, number 4, it looks a little bit different because my bases aren't technically the same. And I know that you could probably already see 7 to the second equals 49. So I know that x equals 2. But I want to use a relating the bases for later, for when our problems get a little harder. So what I'm going to do is say 7 to the x on the left, and I'm thinking, how can I write 49 with a base of 7? And that is 7 squared. Okay, so all I've done is I've changed 49 for 7 squared. Now I can say, oh, look, 7s are equal, so x has to equal 2, which works exactly with what we said it was going to. So that's kind of what we're thinking when we go to number 5. 4 to the 3x equals 8 to the x plus 1. Those bases aren't the same, but we can make them the same because 4 can be written as 2 squared, and then that's raised to the 3x. And then I'm thinking, okay, 2 to the what equals 8? 2 to the third equals 8, and then I still have an x plus 1. So now we just have to be a little careful because we do have equal bases, but we've also got to think about those powers. So I have 2 to the 2 times 3x is 6x, and then 2 to the 3 times x plus 1 is 3x plus 3. You can think about distributing that 3. And then I can go to town solving this equation. I subtract 3x on both sides. And I will put the rest of it over here. I get 3x equals 3. So x is equal to 1. If we think about plugging this in, I could get 4 to the 3 times 1 equals 8 to the 1 plus 1. And I get 4 to the third equals 8 squared. Let's see if that's true. 4 to the third is 64. 8 squared is 64. Check, those two things are equal. Okay, number 6 is similar to the last one. I've already got 2 to the 4x, but 32 isn't an equal base. So I can think 2 to what power could give me 32? Like, is it possible to relate those bases? And it is. So 2 to the 5th, and then I've still got that x minus 1. You can't lose it. And then I can say, if the bases are the same, then I can write 4x equals 5x minus 5. And then I can solve. So I can move this over, subtract 5x on both sides. Negative 1x equals negative 5, and x equals 5. If you want to plug that back in, you are certainly welcome to. You'll see that my left side really can't equal that right side. And the last thing that we have is that logs work exactly the same way. If you have equal bases on your log, then you also have to have equal arguments or equal numbers on the inside. So if I've got ln 4x equals ln 6, I already have the logs the same. So the things that have to also be the same are 4x and our 6. So we'll set them equal to each other. 4x equal to 6. Divide by 4 on both sides. And x equals 6 over 4, which is 3 over 2, or we could say 1.5, however you want to say that. And the last one, I've got log base 5 of x equals log base 5 of 3x minus 4. We already have log base 5 on both sides, so it has to be true is that x has to be 3x minus 4. If those are the same, then our entire equation is the same. Subtract 3x on both sides. Negative 2x equals negative 4. Divide by negative 2 on both sides. And x is 2. If I am going too fast for you on the solving part, you need to go back and do some of these solving problems, just linear equations. So you can pause the video, you can retry these problems, but this is the kind of thing I'm expecting for relating the bases. If you can write the bases equal, then you can also set up a new, simpler equation. There is one more way to write or to solve equations with exponents and logarithms, and that is by using PEMDAS backwards and the fact that logs and exponents are equal. So what I can do is I can go to 2 to the x equals 7, and I want to first see, can I write 7 as a base of 2? Well, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. So there's no way to write 7 as a base of 2. So what I want to do is think, okay, I'm in exponential form. what if I wrote this in logarithmic form? So if I did that, I'd say log base 2 of 7 equals x, because our logs always equal our exponents and our bases always equal our bases. So if you need to go back and look at rewriting logs, that's an 8.4. Now this, I can actually plug straight into my calculator, because log base 2 of 7, if we use our change of base theorem, is log 7 over log 2. And if that seems unfamiliar, go check out 8.5. The end of that video is change of base theorem. So if I plug that into my calculator, I can do that right now. Make sure you close the parenthesis, log 7 divided by log 2. Hit enter and I get 2.807. So that's my final answer. What I'm really looking for is, can I find something that I can actually plug into my calculator? So if I do 10, this is pretty much exactly the same. 4 to the x, I can't plug into my calculator. But if I remember that logs and exponents are inverses, that they undo each other, I can rewrite our log as our exponent. So log base 4, because our bases have to match, of 15 equals x, because our logs always equal the exponents, which is right here. And then I can say x is log 15 over log 4. Don't forget to close those parentheses. So I'll do that right here. Log 15 divided by log 4 is 1.953. When you're doing this, just make sure that you really are plugging this into your calculator, closing the parenthesis, being really careful with that kind of thing. Now going on to our second page, if I look at all of these problems, especially like numbers 11 and 12, you'll notice that we can't plug these straight into our calculator, and we also can't immediately change into log form. So what I've got to do is actually do PEMDAS backwards. I'll subtract 4 on both sides, get 10 to the x equals 3, and now I have something that I can write in log form. So I say log base 10 of 3 equals x. I could do log 3 over log 10, that would work. I can also remember that log base 10 is really just log. That's what our calculator knows it as. So if I say log 3, then my answer is x equals 0.477. Moving on to 12, I'll subtract 3 on both sides because I'm trying to get something that I can write in log form. 5 to the x plus 2 equals 22. Don't be thrown off by the more complicated exponent. I can still write this in log form. I write log base 5 of 22 equals x plus 2. Notice that this left side, log base 5 of 22, is a number that I can plug in my calculator. So I get log base, or log 22 divided by log 5, and I get 1.921 equals x plus 2. Okay, I can, if I move this on over, can actually subtract 2 from both sides just by hitting minus 2 in my calculator. It'll store the last value, and I get x is equal to 0.079, and that's a negative. Okay, so when you're solving these, you're just looking for a point where you can plug something into your calculator. Once you do that, then it's a more simple equation to solve. So doing this right away will help you, I think, see what your next step is. Number 13, we've been plugging a lot of things with log into our calculator, but now we're in log form and I have an x inside of my log. So that's going to be an issue. So instead, I'm going to write this in the other form, okay? Because logs and exponentials, they can go back and forth. They undo each other. So I've got a base of 5, my exponent is 2, and the last piece of the puzzle is 3x plus 1. Notice on the left side, 5 squared is something that we know. We can plug it into our calculator. Hopefully we know it in our heads. 25 equals 3x plus 1. 3x plus 1 is actually a pretty easy equation to solve. Subtract 1 on both sides. 24 equals 3x. Divide by 3 on both sides, and x is equal to 8. See if you can do this one if you want to pause the video. I have a base of 4. Power is 2 equals x plus 3. 4 squared is 16. And now this becomes an easy equation. I subtract 3 on both sides, and x is equal to 13. Just a few more left. Remember that if you are in exponential form, you can go to log form. If you're in log form, you can go to exponential form. It's just back and forth. So 15, I've got a base of 5. My power is 2 equals x minus 4. So 5 squared, we already said, is 25. And then I can add 4 on both sides. So 29 is equal to x, or x equals 29, either way. You'll notice that we're getting a lot of different types of answers. We're getting large numbers like x equals 29. We got some small numbers like negative 0.079. You might get a huge number like a million. You might get a really, really small number. It is okay to get all of these weird types of numbers because remember that x can just be any real number, anything that I can put on the number line. So don't be thrown off there. Number 16 is kind of a weird one. I have e to the x. Now, e on your calculator, remember e is approximately equal to 2.71-ish. So this is like 2.7 to what power gives me 9, okay? So what I'm going to do is I'm going to rewrite this in log form. Log base e, because e is just a number, that's okay, of 9 equals x. Really, I could do log base, or log 9 over log e, but remember that log e is something that our calculator knows. It's natural log, ln. So ln 9 equals x. And x equals 2.197. So this is one that I think will be a little confusing if you see it like on a worksheet or something like that. So I would maybe star it and just remember that e and natural log go together. Okay, number 17. We can either do, so for these last two, I'm going to give us a choice. We can either do PEMDAS backwards, or we can go back to what we did at the beginning of the lesson, which is relating the bases. I think this one's going to be easiest if we relate the bases. Notice that both sides have a base, whereas our other problems, we only had like one side having a base, so like number 12, or one side having an exponent. So here, I want to think, okay, 9 to the 2x equals, and then can we write 81 with a base of 9? Okay, so this would be 9 squared to the 3x minus 2. So now our bases are the same, so it needs to also be the same are our exponents. I've got 2x is equal to 2, don't lose this 2, times 3x minus 2. Or you can distribute right away and get 6x minus 4. So this is 2x, 6x minus 4. And then we can kind of go to town with our solving. Subtract 6x on both sides. Negative 4x is equal to negative 4. Divide by negative 4 on both sides. And we get x equal to 1. Now, if you plug this in up in the original problem, I get 9 to the 2 times 1 is 9 squared, or 81. On the right, I get 81 to the 3 minus 2, which is 81 to the first, so both sides are equal to 81. So this last one too, we can choose either relating the bases or doing PEMDAS backwards and changing forms. I'm actually going to start by subtracting 8 on both sides and then see if we can relate those bases. So we'll get 10 to the 5x plus 4 is equal to 27. And notice that 10 and 27 are not going to be able to be related by a base of 10 or base of anything else. So I'll write this in log form. Log base 10 of 27 equals 5x plus 4. Now this seems a little intimidating because we have so much going on the right side, but remember that log base 10 of 27 is a number. In fact, it's the number log 27 equals 5x plus 4, since log base 10 is just log. So I can say in my calculator log 27 is 1.431, 5x plus 4, and then I can solve. I can subtract 5 on both sides, and I get, subtract 4 rather, negative 2.569 equals 5x. And just in my calculator, divide by 5. So I get negative 0.514 equals x. So those are the two ways to solve these problems, either relating the bases or PEMDAS backwards and changing forms. I think this is really the most important lesson in our chapter because it kind of is a culmination of everything we've done. It's being able to change forms, it is relating logs and exponentials together. So make sure that you do some practice problems here and come and see me if you've got any questions. Bye guys.